This is Paul Fisher from University of Florida. It's a real pleasure to have the opportunity today to talk with you about water treatment technologies. This is the first in our series on water quality with presentations from several experts at different universities and industry. And it's co-sponsored by University of Florida, IFAS Extension, the Water Education Alliance, and our supporting companies, OFA, FNGLA, Society of American Florists, and the Horticultural Research Institute. In this series, we're going to cover some different aspects of water quality. It's a complicated area, and as the quote says, the trouble with facts is that there are so many of them. So what we're going to do is we're going to break down this topic of water quality into 4 parts. I'll be kicking things off today, and we'll have future presentations from Dr. Rob Wick at University of Massachusetts. Rob is a plant pathologist. Lauren Oakey and Sarah White from University of California in Clemson will be talking about slow sand filtration and constructed wetlands, more ecological approaches to water treatment. And Bill Arrigo will finish out the series talking about nutritional aspects of water quality, such as alkalinity, EC, boron issues, and so on. The points that I'm going to cover today are, first, the importance of water quality. Second, the idea of matching this water treatment technology or system to your goals or the specific problems you're trying to deal with. How to choose between different sanitizing agent possibilities. And finally, focusing in on flood floors and benches, sub-irrigation systems, where treatment of water with such rapid water movement is really quite challenging. Now, when we talk about water quality, there are chemical aspects, which we're very familiar with as growers, the EC, electrical conductivity, the specific salt levels that you get back from a lab analysis, alkalinity, which you can think of as dissolved limestone in the water. All of those are going to affect the plant health. There are also physical aspects of water quality. So how much organic loading, peat particles, soil, suspended solids, and so on are in your water source. And there are biological aspects of water quality as well. We think mostly of disease management and controlling pathogens in our water. Algae can certainly be an issue in situations such as plant propagation. And anyone having drip irrigation, micro irrigation systems, biofilm and clogging of nozzles can certainly be an issue. The reason that we're focusing in on this topic is that in agriculture, we're competing for high quality water with urban users and other industries. So these high quality sources, such as municipal treated water and well water, are less and less available to growers. So we need to become our own water treatment specialists and deal with potential problems from lower quality water that may be coming from capturing water in ponds or lined tanks, and also reclaimed water from municipal sources which is partially treated. Now, of course, recycled water and water taken from the furthest outlet away from the source in a greenhouse or a nursery, it's going to be lower quality than the water that's coming straight out of the tap from a municipal supply or well water. And so that means that we have a high organic load, quite often a salt issue or an alkalinity issue to deal with, and a lot of potential for spreading spores of pathogens or algae or other microbes. Here's some example of some data. This is work that was done by Dustin Metter, who's a PhD student here at University of Florida. The arrows point to different sampling points where we took water samples from different nurseries around the United States, and Dustin sampled at different places in the nursery. The reason that I want to show you this is these would be similar types of sampling points that would be useful for you. The source water as close to as possible where that water is entering into your operation, whether it's a tap or a pond. Any holding areas such as tanks. Here's a sub-irrigation tank from a flood floor. The furthest outlet away from the water source. Here we're looking at a dripper, it could be on a irrigation boom and so on. On the floor or bench itself, where you're going to get plant parts and peat material and so on. and also catchment ponds. So if we look at the water quality in those different areas, let's just take one parameter. This is a biological parameter. It's measuring aerobic bacteria. These are bacteria that will grow in an aerated, air-rich environment, which is typical of irrigation water in a pond, say. And we've got our different types of sample: the source, furthest outlet, tank, ebb and flow, and pond, and the colony forming units per milliliter. So this is how many of these bacteria will grow in 1 cubic centimeter of water. Now the source waters, which are mostly well and municipal supplies, are very clean. But as we go through to a furthest outlet away from that source, we're seeing an increase in bacteria because of biofilm. This is the microbes lining the inside of the piping. And anywhere where there is a catchment of that water, whether it's a concrete-lined tank, an ebb and flow bench or flood floor, or out into an uncovered outdoor pond, we get very high bacterial loads. And if the recommended levels are below 10,000 colony forming units per milliliter, once you're up above that number, especially up above 50,000, then you have very high clogging potential that small emitters are very likely to become clogged. Now, as I mentioned, we tend to think of water quality primarily in terms of nutrients, pH and alkalinity. And we're familiar also with the problems of high water alkalinity leading to high pH in the container substrate, lack of iron, and iron deficiency, as you're seeing these pale symptoms and necrosis in these new leaves of Calibrachoa, an iron inefficient plant. High EC, or electrical conductivity, which is the total measurement of all of the dissolved salts, and specifically junk ions such as sodium and chloride, will tend to increase the EC in the growing medium and lead to salt burn of roots and accumulation of those salts, especially in older leaves, as you're seeing in this penta here. Water pH and EC also affect the efficacy of sanitizers. Okay, so here's an example of, we typically think of pH, EC, and so on in terms of plant health, but it also interacts with chlorine. Along the horizontal axis, we're seeing increasing pH. On the vertical axis, there is the percentage of all of the chlorine in a bleach solution here. And that bleach could be in one of two forms dissolved in the water: hypochlorous acid, which is an effective sanitizer. That's what has the killing power against pathogens and microbes. Or hypochlorite at high pH, which is a weak sanitizer. So, for example, with chlorine, you'll typically get a recommendation of an ideal pH range around 6 to 7.5, so that most of that chlorine is in the strong sanitizer hypochlorous acid form. pH affects a lot of solubilities and chemical forms of the pesticides that we work with. In case of EC, one example of where that's important in terms of sanitation is in copper ionization. When the EC is low, there's not much electrical charge, by definition, that passes through water, so it is harder to ionize copper and get the parts per million that you desire. Another aspect of water quality is this high organic matter. Here we're looking at peat and perlite loading up a return tank from a flood floor greenhouse. And that's important also in terms of the efficacy of all of the sanitizers that we're working with. Here we've got a graph that shows the number of grams of peat in 1 liter of irrigation water. And on the vertical axis, we're looking at what percentage of the active ingredient is left 1 day after we mix that peat into the water. Green shield is an example of a quaternary ammonium chloride product. You can see that how much active ingredient is left after a day decreases quickly with increasing peat. Free chlorine, from whether it's from gas chlorine, sodium hypochlorite, calcium hypochlorite sources, is extremely sensitive to organic load. Here's an activated peroxygen product, xeritol. Xylitol's got two active ingredients, hydrogen dioxide and peroxyacetic acid. Both of those levels will go down with increasing organic load. So filtration and removal of organics is essential to the efficacy of every one of these sanitizers that we work with. Plant pathogens is probably the most important biological aspect of water quality as growers that we deal with. There are many plant pathogens identified in irrigation water, Phytophthora, Pythium, fungi, bacteria, viruses. Probably the most important one we typically deal with are zoospores, which are the active, infective swimming spores of the water molds Phytophthora and Pythium. Another aspect of biological water quality is the microbial density or biofilm, the gunk that lines the insides of our piping. These are a cutaway of some different pipes here. The photo is taken by Dr. Peter Conjoyan. What we're seeing in the middle line here is this is clear water passing through an underground pipe, and when we add a nice nutrient source, our fertilizer, then we have an algae biofilm complex that develops even in the absence of light. Out in the greenhouse, we get clogged drip emitters where if we look closely, we can see that there's this goop that's forming that is a complex of different microbes. Another reason that we should be concerned about biological water quality is if you're producing any herbs or vegetables or fruit crops, which more and more greenhouse and nursery growers are doing now. Because it's not just the plant pathogens that are important, but it's also food safety pathogens such as E. coli that are obviously critically important in terms of producing an acceptable crop.